Hey, Honors Physics. Here is the complement to the top of page 23. Here's a new energy problem that has a unique situation. Let's make sure we're clear on this. So we have a snowboarder or a skateboarder that starts at some height, 25 meters up, and they skid down or they slide down the mountain for a distance, and that distance probably could be determined, but it's not critical to our understanding. But they slide down the hill, but notice there's no friction. Maybe it's perfectly icy, okay, or a smooth surface. Then the friction begins here. So there are two schools of thought on how you might go about solving this. Do you call this a problem where you try to go from A to B, where the change in the potential energy becomes more kinetic energy and the skateboarder clearly would build up some speed? Or do you go straight to this final point? Now, it's labeled B, but we're going to call it C because depending on your school of thought or your strategy, you can actually do it either way. But I think the easier way to do this will be to go straight from A to C. And that's referred to as a state. Oops, let's update a little bit of that. A state function. No, not state as in political, but rather, and we're going to update this so we can actually read it better. My fault. Let's put in this, a state function. A state function means a process or a change in a system where the mechanism how you get from A to B, or in this case, A to C, does not matter. You just have to know all of the information about A and all of the information about C. And of course, in this case, that there is going to be some work, non-conservative, due to this hill. So let's go about and tackle this the best we can. Let's start with total mechanical energy at the top of the hill, at the very highest point. Then we're going to account for the work non-conserved on only this part of the hill. It doesn't matter that it doesn't begin at the top. We're just going to calculate how much energy is lost. And then we're going to examine the total mechanical energy at the final, or at C. And here we are at A. And the skateboarder clearly has PEG because there's some height. And there's also some kinetic energy because there's some motion, there's some velocity. And then there's going to be the force of friction times the distance along the hill. We don't know the distance along the hill yet. But notice the distance along the hill. The only distance we care about is the distance where there's friction, from the 20 meters high mark down to the bottom. And then let's add in cosine of 180 degrees because the friction's backwards, the displacement is forward. And then at the very bottom of the hill, there's, of course, some kinetic energy. So let's do some plugging in. mgh plus 1/2 mv squared. Now, the friction force on hills, kind of challenging, mu times mg cosine 30. There's my normal force times my distance, and the cosine 180, let's just simplify that down to -1. Okay, well, we'll do some plugging in on our calculator and get our mgh. Let's do that. We have a mass of 60 times g of 9.8 times a height of 25 meters at the highest point. I get 14,700 joules. And for a velocity squared times mass times 1/2, I get 750 joules. Okay? So those are the total mechanical energy at the start. And now let's start plugging in the values we know. The mu is 0.4. The m is 60 times 9.8 times cosine 30. Cosine 30 is 0.886. We're just going to leave it as cosine 30 because we'll do that on our calculator. Now the distance along the hill. I see a triangle that has a height of only 20 meters, a angle of 30 degrees, and we'd like to find the distance along this hypotenuse. So therefore, we're finding the hypotenuse, as I said. So sine of 30 equals 20, the height of 20 over d. And it was a student in E block who said, well, you could use sine or you could use secant to flip that over, the inverse of sine. Most people are not as familiar with those, so you're welcome to do it if you want. I'm going to simply take 20 and divide it by sine of 30. And I'm going to get a distance of 40 meters. So 40 meters times negative 1. On the other side of the equation, we don't know the velocity, but we know the mass is 60. So we can just make this 30 v squared. Now, I did have a couple of students say, why didn't we cancel out the 60 kilograms throughout the whole problem? You're welcome to do that. But as it turns out, it doesn't save that much time when you're in the weeds like this. Or at least, I don't think it does. It's almost like one more thing to remember. To leave out the mass, that is. Okay. When I crunch all of this, let's do that. I'm going to do that twice because it's a long calculation. 0.4 times 60 times 9.8 times cosine of 30 degrees of the hill. That finds our normal force, of course. And then the distance along the hill is 40 meters times negative 1. Negative 8,147.57 joules. So when we crunch this all together, 14,700 plus 750 minus 8,147.57, and then we divide both sides by 30, divide all of this by 30, I got a total of 243.41, but that's equal to v squared. So we need to do a quick square root of the 243, and we get a velocity of 15.60 meters per second, or about 16 meters per second. Now, that's the quick way to solve it, where you go straight from A to C, but you factor in the work that happened through a portion of the hill, not the whole hill, but a portion of the hill. Quite honestly, the friction could have started anywhere. We could have, as long as we know the height where it starts, then we can find the distance, okay? Now, I did have a couple of people say, well, why not go A to B? Well, we can do that. We can do mgh plus 1/2 mv squared equals mgh plus 1/2 mv squared, and try to find the velocity at B so that you could then use that velocity to go into the work non-conservative. But as it turns out, it's going to be probably just as much work. Now, I do see that the masses cancel, and this is totally optional if you want to follow this step along, but 9.8 times a height of 25, I get 245, half of the velocity squared, 0.5 times 25, 12, sorry, let's try that again, half of 25, and I get 12.5, and now G times H. This is the lower height. This is the height of 20, so 9.8 times the height of only 20 meters, 196, and then that leaves us with the unknown velocity. So let's finish that. 245 plus 12.5. There's a decimal in there. That's a little hard to read. 12.5 equals 257.5 minus the 196 when we move it to the other side. Multiply that by 2 to get rid of the half, and then let's square root that. And you notice it comes out to be a V at B of about 11.09 meters per second. It has built up some speed from 5 to 11. It's making some headway. Now we have to go from B to C, but we have to conserve energy. So there's mgh plus 1/2 mv squared, but there's work non-conservative between B and C. And then at C, there's only 1/2 mv squared. There's only kinetic energy. So I'd like to simplify and cut out my masses, but I have to be very careful to make sure that I cut out my mass from my expression that's up here. I'm not going to rewrite the expression. I'll be candid. We're just going to drop out the 60 when we calculate it here. But there is really a mass in every single term. So let's plug in. But we realize that we've already done this work. We already have the 196. We already have the 1/2 mv squared. I forgot to write the squared, but we'll fix that. 1/2 times the velocity, 11.09, quantity squared, 61.49. Now let's deal with the work. The work formula, right up here, mu times mg cos theta times 40 times -1, but we're going to drop out the m. So I'm just going to describe it as I put it into my calculator. 0.4 times 9.8 times cosine of 30 times 40 times -1. And I get -135. 0.79. We should probably keep those because it's not close to exactly 135. And then 1/2 of v squared. So 196 plus 61.49, but minus the 135, the negative work due to friction, equals 121.7 times 2 square root the answer, and I get 15.60 meters per second. It is proven that it does not matter whether you go from A to C or A to B to C.